In this video, I'm going to give you some hints about homework 4. The first problem is number 2 on page 168. Proposition 15 from Euclid's book, Elements, the first book of Elements. And we know Euclid, the Elements has 13 books, and a link to these 13 books is posted on Blackboard. If you are interested, you can kind of go through them. So this one is talking about two intersecting lines. One cuts another, and they make 4 angles we can see in the picture here. We call them alpha, beta, gamma, and there's another one. These two lines intersect at the point P. We call it P. So we want to prove two vertical angles are equal. Vertical angles, we mean these two angles, for example, alpha and gamma, or beta and the other one. We only need to prove one of them. So if we want to, you can prove alpha is congruent to gamma. Clearly, we know this as a probably as a fact, but we are able to prove it very easily. And here I'm going to give you a similar example to this problem, how to write a proof. If you had Math 1 through Math 306, you may have learned how to write down a proof. If you had a Math 120 series, in Math 122, we have also learned some properties of geometry. So here, a similar example is this: to prove that the supplementary angles of congruent angles are congruent. Supplementary angles, that means if you have two angles, we add them together, we can get 180. That means they are supplements of each other. So I drew two pictures here. The first one is angle BCD, that's alpha. And the second angle is angle HFG, that we use alpha prime to denote the measure of angle HFG. These two angles, they are congruent. So that means their measures are equal. So alpha equals alpha prime. And alpha and beta, they are supplementary angles of each other. That means from the picture you can see, because ABC is a straight line, so alpha plus beta is 180 degrees. That's the definition of a straight angle, 180. Similarly, alpha prime, from the picture, alpha prime plus beta prime is 180. Well, we want to prove if alpha equals alpha prime, beta must be equal to beta prime. So this is a question kind of similar to the homework assignment. What we need to prove when we in order to prove beta is equal to beta prime, first of all, we notice alpha plus beta is 180 degrees by the definition, because beta is the supplement of alpha. So we subtract alpha from both sides. We get beta equals 180 degrees minus alpha. Similarly, alpha prime plus beta prime is 180 degrees. That's because beta prime is the supplement of alpha prime. And then beta prime equals 180 minus alpha prime. We subtract beta prime from both sides. Now, if we look at these two equations, beta and beta prime, we want to show beta is equal to beta prime. If we look at the right side, they're both equal to 180 minus something. The difference is one is alpha, the other is alpha prime. But we know at the beginning, that's given, alpha is equal to alpha prime. So that means 180 minus alpha is equal to 180 minus alpha prime. because alpha and alpha prime are equal. And of course, 180 minus alpha is beta. 180 minus alpha prime is beta prime. So that means beta is equal to beta prime. So if we go back to the homework assignment, it's kind of similar. If you want to show alpha is congruent to gamma, we notice alpha and beta, they form a straight line, these two angles together. So it's a straight angle 180, and also beta and gamma, it's 180. So we can similarly prove alpha is congruent to gamma. And the next problem, second problem, it's on page 182, number 1E. And this one section is talking about some of the results from Euclid's book, Number Theory. If this vertical line means divides, so if A divides B and C divides D, then we want to prove AC divides BD. So this is the homework assignment. If you had 306, this is one of the questions, one of the problems in number theory we have talked about, or you learn a number theory class. So I'm going to give a similar example. This example is on page 172. There are 6 propositions. We're going to prove this number 6. Actually, the textbook also has the proof. If A divides B and A divides C, then we want to show A divides B times the number X plus C times the number Y. And X and Y, they are any integers. When we do these proof questions, we cannot pick a number for A, B, C, D, because they represent any numbers. Like we had in algebra class, A, B, C, D can be anything. Similarly, the question here, we cannot assume alpha is a certain degree of alpha can be any degree, can be 120, for example, or alpha can be 90, alpha can be 30. And also, but if whatever alpha is, we want to show beta is the same as alpha. So in the whole proof, we shouldn't assume they are having any certain degrees. But the only thing we know is the straight line must be 180 degrees. Now let's look at the proof here. X and Y are any integers. It may be 2 or 4 or even negative numbers. And A, B, C are any integers. From the definition of when we say, for example, but we can think about the definitions when we say 2 divides 6, what does it mean? That means if when we say 2 divides 6, we mean 2 divides 6 evenly. That means the remainder is 0, because 6 divided by 2 is 3, and the quotient is 3, and the remainder is 0. And so when we say, because we know A divides B, that means there exists an integer R such that B equals A times R. If we think about, if this is difficult for you to understand, you can think about example 2 divides 6 evenly. What does it mean? That means 6 can be written as 2 times 3. So the same thing here. A divides B. That means B, the big number, can be written as A times some quotient R. What R is depends on what A is, what B is. But if A divides B evenly, this R should exist. Similarly, if A divides C, we can find an integer S satisfying C equal to A times S. But we want to prove A divides BX plus CY. That means when we divide A by BX plus CY by A, the remainder should be 0. We know B divided by A has the remainder is 0, and the remainder of C divided by A is 0. How to prove that? So from the assumptions, we already get these two, and we compare these two equations, and with what we want to prove, BX plus CY is getting close because we have B here and C here. If I multiply the first equation by X, both sides, I will get bx equals arx. So that's what I have. Bx is arx. So I replace b with ar here. And similarly, I multiply y both sides. Or I can say I replace c with as. So that's another way. We can either say multiply y both sides, we get cy equals asy. Or we can just start with bx plus cy. Bx plus cy equals, replace b with ar here, plus replace c with as. So as times y. And then we continue, we can use the associative property. Arx, we can move the parentheses to rx, and similarly move the parentheses from as to sy. And notice they both have a in common, so I factor out a. Then we have rx plus sy. And we need to explain. So we are able to write bx plus cy as a times something. If we can prove rx plus sy is an integer, then that means that's the quotient. So bx plus cy divided by a has remainder 0. And clearly rx plus xy is an integer because r is integer. Rs are both integers because rs are both quotients of a divided by c. I mean, r is the quotient of a divided by b, and s is the quotient of a divided by c. Of course, r and s are both integers. Similarly, and not similar because it's given. Integers, x and y are integers. So integer times an integer is still integer, plus another integer is still integer. So that's why rx plus xy is integer. So that's the quotient when bx plus cy divided by a. And that means the remainder is 0, or we can say a divides bx plus cy evenly. Then next, homework assignment on page 182, number 16, Euclidean algorithm. I will give you example on next page. We're gonna give you a quick hint about the first problem 1D on page 208. We want to prove the surface area of a sphere is 4 times the area of a great size circle. If we draw a sphere, the great circle is the equator. Any circle that has the center the same as the center of the sphere. So if you look at the picture, the red one here, the hint is the surface area of sphere is SA equals 4 pi r squared, and r is the radius, and we know the area of circle. What the area of circle is, it's pi r squared. So you clearly can say the surface area is 4 times the area of a great circle. Next, I'm going to give you example. This is the example on page 182. The homework assignment number 16 on page 182. But this problem is on page 175. We want to find the greatest common divisor of these two numbers.